So, in this tutorial video, I will talk about the Noether Normalization Lemma. Let me first state the Noether Normalization Lemma. Noether Normalization Lemma. Let K be a field and A, this is not equals to 0, be a finitely generated K algebra. Then there exist some elements, say y1 up to yr inside A, which are algebraically independent. It means that the K algebra generated by these elements y1 up to yr, this is isomorphic to the polynomial algebra in R variables. So, it means this. Algebraically independent such that A is integral over this this algebra K y1 up to yr. So, this is the Noether Normalization Lemma. Now, proof. Since this A is the finitely generated K algebra, so we can write okay. So, there exist some elements x1 up to xn say inside A such that they generate A as K algebra. Okay. Now, if these elements x1 up to say xn are already algebraically independent, then we have nothing to prove, right? We have nothing to prove. So, let us assume that. So, we may assume that this x1 up to xn, they are algebraically dependent. Okay. It means that is there exists a non-zero polynomial f say inside this K t1 up to tn in n variable such that f x1 up to xn, when we evaluate, it will be 0. Okay. Now, from here it is immediate that degree of f has to be strictly greater than 0. Now, a claim. There exist some elements z1 up to say zn minus 1 inside A such that A we can write as the K algebra generated by this z1 up to zn minus 1 and xn, and xn is integral over this K algebra K z1 up to zn minus 1. So it also implies that this A is integral over this k z1 up to zn minus 1. Okay. If we can show this claim, then it is this Noether normalization lemma follows, right? Okay. Now, for proving this claim, first consider capital N to be this degree of f plus 1. Okay. And we define Zi to be xi minus xn to the power n to the power small n minus I for each I from 1 to n minus 1, and we define a polynomial f which is small f of t1 plus tn power capital N power n minus 1 up to tn minus 1 plus tn power n comma tn. So this is also a polynomial in n variables k t1 up to tn. Now look, the way we define this capital F, it says that f z1 up to zn minus 1 comma xn, this is equals to 0, because this small f is means when we evaluate this small f at x1 up to xn, then it will be 0. So from there it follows that this capital F, when we evaluate at z1 up to zn minus 1 and xn, this will be equals to 0. Okay, this is easy. This is just follows from the observation, means how we define this capital F. Now observation, each monomial say A times this summation t to the ti to the power ti to the power not summation, sorry, this is product ti to the power bi, I runs from 1 to n. In f, small f gives rise to various monomials in capital F, right, among which A tn to the power bn plus bn minus 1 n plus up to b1 times n to the power n minus 1 has the highest degree. Okay. Okay. Now by division algorithm, means division algorithm means when we means divide integer, an integer by a positive integer, we get a unique quotient and unique remainder. By division algorithm, we see that for different monomials, say this A times this product ti to the power bi, I runs from 1 to a, n in f, we get different values of this bn plus bn minus 1 n up to b1 n to the power n minus 1, right. Now the highest order monomial in f is among the monomials in this capital F, is among the monomials of the form a times Tn to the power Bn plus Bn minus 1 n plus up to B1 n to the power n minus 1. Okay. Then we can write this capital F as some constant times Tn to the power degree of this capital F plus some terms of degree strictly less than degree of capital F. Okay, here B is non-zero. Then we get this 1 by Bf when we evaluate at z1 up to zn minus 1 comma t, this if we consider this polynomial in one variable whose coefficients are from this k z1 up to zn minus 1. Okay, so this is a monic polynomial. This is a monic polynomial because we did we multiplied with 1 by b, so its leading coefficients will be 1, right. So it says that 1 by b f when we evaluate at z1 up to zn minus 1 comma xn, this is equals to 0. This okay, this we already seen. So this is a equation. So from here it follows that this xn is integral. This xn is integral over this k algebra k z1 up to zn minus 1. So it proves the claim, right. Now if we repeat the process and observe that the integral dependence is transitive. Is transitive. Okay, we repeat the process to get the result, the main result. So we are done. So the proof is a little technical, but it is not too difficult. Okay. Now I will state a generalization of this Noether normalization lemma, and the proof is all means similar to the proof of the normalization lemma, the Noether normalization lemma. Let me first state the generalization. Generalization normalization. Let D be an integral domain and R not equal to 0 is a finitely generated D algebra. Here instead of a field we are taking an integral domain. Okay. Then there exists a non-zero element C inside D such that this R localization at C, this is integral over a polynomial ring D localization at C T1 up to say Tr. So this is a generalization. For the proof we have to just follow the same proof, just we have to here observe that here we took 1 by b, we multiplied 1 by b. Here we could do that because this k is a field, so each non-zero elements is invertible. But when we are considering an integral domain, we have to find a non-zero element where we can localize it. We have to take localization, then we can invert it. Okay, so that's why we need this localization at C. Okay, now I will state some remarks, make some remarks. Let K be a field and A an integral domain which is also a finitely generated K algebra. Okay. So Noether normalization lemma states that there exists y1 up to yr inside A algebraically independent such that this A is integral over this K algebra generated by this y1 up to yr, right. This is what this Noether normalization lemma states. Now if this A is a field, say if this A is a field, then from the properties of integral dependence we can we have already seen in the first few lectures that this will be also a field. This follows from the properties of integral dependence. Okay. Now this implies that this is equals to K, because a polynomial ring cannot be a field unless it is equals to the field itself. Means a polynomial ring in R variables where R is strictly greater than 0, it is not possible, it cannot be a field. So the only way it can be a field if this K y1 up to yr, this is equals to K, right. So this means that this A is integral over K. So it means that this field of fraction of A, this is algebraic. over this field K. So, this is first remark. Remark 2, say A is integral over K y1 up to yr, this we already know. This implies that this field of fraction of A, this is algebraic over this field K y1 up to yr. Okay. So, this implies that from the definition of transcendence degree, it follows that this transcendence degree of this fraction field of A over this K, this is equals to nothing but R. So, this is second remark. Now, third remark, by going up theorem, dimension of A is equals to dimension of K y1 up to yr, because this A is integral over this K y1 up to yr. So, from going up theorem, it follows that their dimensions are same. So, this is equals to R. This follows from dimension theory result, from dimension theory. Now, this is equals to the transcendence degree of the fraction field of A over K. So, these are some remarks. Okay. Now, at the end, I will just state some important results in dimension theory, which we will need to solve some problems in algebraic geometry. So, we need these results. I will state some important results. Important results in dimension theory. Okay. First, let K be a field, a finitely an integral domain, which is also a finitely generated K algebra. P a prime ideal, then this height of this prime ideal P, this is nothing but the dimension of the local ring A localization at P, okay, plus dimension of A mod P, this is equals to dimension of A. So, this is one result. Now, let A be a Noetherian ring. Say A1 up to AN, inside A be some elements and P be a minimal prime ideal containing these elements A1 up to AN. Then the height of this prime ideal P, this is less or equals to N. This is called Krull's dimension theorem. Krull's dimension theorem. Now, second, if A is inside A is neither a zero divisor nor a unit, then every minimal prime ideal containing A is of height 1. Okay. So, this is called Krull's principal ideal theorem. This is called Krull's principal ideal theorem. Principal ideal theorem. Now, number 3, dimension of A, say some T1 up to Tn. This is equals to dimension of A plus n. Means this here this T1 up to Tn are independent variables. So, this is polynomial ring in n variables, coefficients in A. So, it will be equals to dimension of A plus n. Now, third, let A m be Noetherian local ring, then dimension of A, this is less or equals to dimension of m mod m square. This is a k vector space. It follows from the this is a finite dimensional k vector space. It follows from the Nakayama's lemma. This is k vector space where k is and this is finite dimensional, where k is this A mod m, the residue field. Okay. Now, fourth, a Noetherian domain is UFD if and only if every height 1 prime ideals is principal. So, these are some important results in dimension theory. Okay, let's stop here. Thank you.